Before we begin this calm journey through one of the universe's most profound mysteries, if you're finding comfort in this space, please consider subscribing to the channel and leaving a like. It helps more people discover these peaceful explorations of science. Your support means everything, and it allows us to continue creating this content for you. Now let's settle in together and explore something truly remarkable. The universe exists. You exist. Everything around you, from the device you're holding to the stars scattered across the night sky, is here, tangible and real. Yet, according to our best understanding of physics, none of this should be possible. The mathematics that govern the smallest particles, the equations that describe how matter and energy interact at the most fundamental level, all point toward the same impossible conclusion. The universe should have destroyed itself in the first fraction of a second after it began. This isn't speculation or philosophical musing. It's a genuine problem that sits at the heart of modern physics, a quiet crisis that scientists have been contemplating for decades. The universe shouldn't exist, yet here it is, vast and ancient and filled with galaxies, stars, planets, and life. Something went differently than our theories predict. Something happened that we don't yet understand. In this gentle exploration, we'll walk through this mystery together, slowly and carefully. We'll examine what physics tells us should have happened in the universe's first moments, why that prediction conflicts with reality, and what scientists are doing to solve this profound puzzle. There's no rush, no urgency. We'll take our time, letting each concept settle before moving to the next. So find a comfortable position, let your breathing slow, and join me as we explore one of the deepest questions in all of science. Why does anything exist at all? The universe that should have vanished. The beginning of everything.
Let's start at the very beginning, in the first moments after the Big Bang. Imagine, if you can, a time when there was no space as we know it, no time ticking forward, no matter forming into atoms and molecules. Everything that would eventually become our universe existed in a state so different from anything we experience that it's almost impossible to describe with ordinary words. About 13.8 billion years ago, the universe began. Not from nothing exactly, but from a condition of such extreme density and temperature that our usual understanding of physics breaks down. In that first infinitesimal fraction of a second, the universe was unimaginably hot and dense, filled with pure energy that would soon begin transforming into the matter we see today. As the universe expanded and cooled, that energy began converting into particles. This is where our story truly begins, because the process of creating matter from energy reveals something unexpected, something that leads directly to the mystery we're exploring. Matter and its mirror. In the realm of particle physics, there's a beautiful symmetry that governs how matter behaves. For every type of particle that exists, there's a corresponding particle called an antiparticle. These pairs are like mirror images of each other, identical in almost every way except for one crucial property: their electric charge is opposite. Take the electron, for instance. It's a tiny particle with a negative electric charge that orbits the nucleus of every atom. Its antiparticle is called a positron, and it's identical to an electron in mass and behavior, but it carries a positive charge instead of a negative one. The proton, which sits in the nucleus and carries a positive charge, has an antiparticle called an antiproton with a negative charge. Even particles with no charge, like neutrons, have antiparticles that differ in other quantum properties. This pairing extends to every particle we've discovered.
Quarks have antiquarks. Neutrinos have antineutrinos. Every fundamental particle has its antimatter twin, its opposite partner in the cosmic dance. Now here's where things become interesting and where the first hints of our mystery begin to emerge. When a particle meets its antiparticle, something dramatic happens. They annihilate each other, completely and utterly. Both particles vanish, and in their place, pure energy appears, usually in the form of photons, particles of light. This process is perfectly symmetrical. If you create matter from energy, you create equal amounts of matter and antimatter. If you bring matter and antimatter together, they destroy each other completely, returning to pure energy. It's one of the most fundamental symmetries in physics, a balance so perfect that it should apply everywhere, at all times, including in the first moments of the universe. The first moments. In the beginning, as energy converted into particles, the universe should have created equal amounts of matter and antimatter. This isn't a guess or an assumption. It follows directly from the fundamental laws of physics as we understand them. Every time energy becomes matter, it produces both a particle and its antiparticle in equal measure. There's no known reason why it should favor one over the other. So picture the early universe, cooling and expanding, its energy crystallizing into particles. For every electron that appeared, a positron should have appeared alongside it. For every quark, an antiquark. For every proton, an antiproton. Matter and antimatter created in perfect equal proportions, filling the young universe. And then, inevitably, these particles would have encountered each other. In the dense, hot soup of the early universe, particles and antiparticles would have been constantly colliding, touching, meeting. And every time they met, they would have annihilated each other, converting back into energy.
This process would have continued over and over in an endless cycle. Energy becomes matter and antimatter. Matter and antimatter collide and become energy again. Back and forth, creation and annihilation in perfect balance. Eventually, as the universe expanded and cooled further, this process would have slowed down. The energy would become too diluted, too spread out to create new particles. And at that point, all the remaining matter and antimatter would have found each other, collided one final time, and vanished. The universe should have ended up empty. No matter, no antimatter. Just a vast expanse filled with nothing but photons, particles of light carrying the energy that once was matter. No atoms would have formed. No stars would have ignited. No galaxies would have spiraled into existence. And certainly, no life would have emerged to wonder about any of this. Yet here we are. The universe we observe. Look around you. Everything you can see, touch, or interact with is made of matter. The air you breathe, the ground beneath you, your own body, all composed of matter particles, electrons orbiting nuclei made of protons and neutrons. The Earth is matter. The Sun is matter. Every planet, every star, every galaxy we can observe through our telescopes, all of it is matter. Where is the antimatter? It's almost nowhere to be found. Oh, we can create it in laboratories. We can smash particles together with enough energy to produce matter-antimatter pairs. We can even observe tiny amounts of antimatter created naturally in cosmic ray collisions or certain types of radioactive decay. But these are fleeting, momentary occurrences. The antimatter appears and quickly annihilates with nearby matter. The universe as a whole is overwhelmingly made of matter. For every billion particles of matter we observe, there might be one particle of antimatter, if that. The symmetry that should have existed between matter and antimatter is completely broken.
The balance that physics predicts simply isn't there. This is the failure in physics. This is the mystery that shouldn't be. According to our best theories, the universe should be empty, yet it's full. There should be no matter, because it should have all annihilated with antimatter. Yet matter fills every corner of space we can observe. Something happened in the first moments of the universe, something that created a tiny imbalance, a slight asymmetry between matter and antimatter. For every billion antimatter particles created, perhaps 1,000,000,001 matter particles appeared. When all the pairs annihilated each other, that one extra matter particle in every billion survived, and from those survivors, everything we know emerged. The scale of the problem. It's worth pausing here to appreciate just how profound this mystery is. We're not talking about a minor discrepancy in some obscure corner of physics. We're addressing the existence of everything. Every atom in your body, every star in the sky, every planet, every galaxy exists because of this unexplained asymmetry. The problem touches the very foundations of physics. Our theories of particle physics, gathered together in what's called the Standard Model, are remarkably successful at explaining how particles behave. They've been tested in countless experiments, and they work extraordinarily well. They predicted the existence of particles years before we discovered them. They explain the forces that hold atoms together and govern how particles interact. But the Standard Model cannot explain why matter dominates over antimatter. The symmetry it describes is too perfect. The balance it predicts is too exact. There's simply no mechanism within our current understanding that would create the imbalance we observe. Some scientists have proposed that perhaps matter and antimatter did end up in equal amounts, but they separated into different regions of space.
Maybe half the universe is made of matter and half of antimatter, with vast empty regions between them. It's an interesting idea, but observations don't support it. We see no evidence of the massive amounts of gamma radiation that would be produced at the boundaries where matter and antimatter regions would meet and annihilate. Others have suggested that the laws of physics might be different in other parts of the universe, perhaps favoring antimatter instead of matter in distant regions we can't observe. But this pushes the question back without answering it. Why would the laws of physics vary from place to place? And even if they did, why do we find ourselves in a matter-dominated region? A gentle look at symmetry. To understand this mystery more deeply, we need to talk about symmetry in physics. Don't worry, we'll keep this calm and simple. Symmetry in physics is about things staying the same even when you change something. It's about balance and equivalence. Think about a perfectly round ball. If you rotate it, it looks exactly the same afterward as it did before. That's rotational symmetry. The ball has the same appearance from every angle. Or consider a perfectly symmetrical face. If you could fold it down the middle, the left side would match the right side exactly. That's mirror symmetry. In physics, symmetries are incredibly important. They're not just aesthetic qualities. They're fundamental principles that govern how the universe works. Every symmetry in physics corresponds to a conservation law, a rule that says certain quantities must stay constant over time. For example, the fact that the laws of physics are the same everywhere in space corresponds to the conservation of momentum. The fact that the laws of physics are the same at all times corresponds to the conservation of energy. These aren't separate facts, they're different aspects of the same deep truth about how reality is structured.
The symmetry between matter and antimatter is called charge conjugation symmetry, or C-symmetry. It says that if you swap every particle in a process with its antiparticle, the process should work exactly the same way. Physics shouldn't care whether you're using matter or antimatter. The rules should be identical. But our universe violates this symmetry. It clearly prefers matter over antimatter. The question is, how? What process in the early universe broke this symmetry in just the right way to leave us with a matter-dominated cosmos? 3 conditions for asymmetry. In the 1960s, a physicist named Andrei Sakharov identified 3 conditions that must be met for the universe to develop a matter-antimatter asymmetry. These conditions are elegant and simple, yet profound in their implications. Let's walk through them gently, one at a time. The first condition is that there must be processes that violate what's called baryon number conservation. Baryons are a class of particles that includes protons and neutrons, the particles that make up atomic nuclei. In most processes we observe, the number of baryons minus the number of antibaryons stays constant. You can create a proton-antiproton pair, increasing both numbers by 1, but you can't create a proton without creating an antiproton somewhere. Sakharov said that to create asymmetry, there must be processes that can change the net number of baryons, creating more baryons than antibaryons, without requiring perfect balance. The second condition is that the processes creating this asymmetry must violate C-symmetry and another symmetry called CP symmetry. We've talked about C-symmetry, the equivalence between particles and antiparticles. CP symmetry combines C-symmetry with P-symmetry, which is about mirror reflections in space. If physics were perfectly CP symmetric, then swapping particles with antiparticles and flipping everything as if in a mirror should give you identical results.
For an asymmetry to develop, these processes must work differently for matter than for antimatter. The third condition is that these asymmetry-creating processes must have occurred when the universe was out of thermal equilibrium. Thermal equilibrium is a state where everything has settled into balance, where energy is distributed evenly and nothing is changing anymore. If the universe had been in equilibrium when these processes occurred, any asymmetry created would have been immediately erased by the reverse processes happening at the same rate. The universe needed to be in a state of change, expanding and cooling, to lock in the asymmetry before equilibrium could erase it. These three conditions provide a roadmap for understanding how the universe might have developed its matter-antimatter asymmetry. But identifying the conditions and finding the actual physical processes that satisfy them are two very different things. What we know works but doesn't. The standard model of particle physics does contain some processes that violate CP symmetry. We've observed these processes in laboratory experiments with certain types of particles called kaons and B mesons. When these particles decay, they show a slight preference for one outcome over its CP conjugate, the antimatter equivalent. This was a major discovery, earning multiple Nobel Prizes, and it showed that the symmetry between matter and antimatter isn't perfect even in our current universe. Physics does distinguish between particles and antiparticles, at least in some circumstances. For a while, scientists hoped that these known CP violations might explain the universe's matter-antimatter asymmetry. Perhaps these same processes, operating in the early universe, could have created the tiny imbalance we observe. But when physicists calculated how much asymmetry these processes could produce, they found it wasn't nearly enough.
The CP violation we've observed in the standard model is far too weak to account for the matter-antimatter asymmetry we see. It would create an imbalance, yes, but one that's billions of times too small to explain why anything exists. This is where the failure in physics becomes most acute. We have a framework, the standard model, that explains nearly everything we can measure about particles and forces. Yet it fails to explain the most basic fact about the universe, why there's something rather than nothing. Looking beyond. This failure tells us something important. It tells us that the standard model, successful as it is, cannot be the complete picture. There must be physics beyond what we currently understand. New particles or forces or processes that don't appear in our current theories. These unknown elements of physics must have been active in the early universe, creating the asymmetry that allowed matter to survive. Scientists call this realm physics beyond the standard model, and it's one of the most active areas of research in modern physics. Researchers are looking for clues in laboratory experiments, in cosmic observations, and in the mathematics of theoretical physics. Some of these ideas involve new particles that haven't been discovered yet.
Particles that would have existed in the early universe, but that are too heavy or too rare to create in our current particle accelerators. Others involve modifications to the fundamental forces, changes to how particles interact that would only become apparent at the enormous energies present in the first moments after the Big Bang. Still, other theories suggest that the answer might lie in the nature of the Higgs field, the field that gives particles their mass, or perhaps in the properties of neutrinos, ghostly particles that barely interact with anything else, or maybe in grand unified theories that attempt to merge all the forces of nature into a single framework.
Each of these ideas is being explored, tested, and refined. Each represents a possibility, a potential answer to why the universe exists, but none has been confirmed yet. The mystery remains open, waiting for the insight or experiment that will finally reveal what happened in those first crucial moments. The cosmic perspective. Let's pull back for a moment and look at this mystery from a different angle. The matter-antimatter asymmetry isn't just an abstract problem for physicists to solve. It's intimately connected to the story of how the universe evolved from a hot, dense beginning into the rich, complex cosmos we observe today. In the first fraction of a second after the Big Bang, the universe was too hot for atoms to exist. It was too hot even for protons and neutrons to form. Everything existed as a soup of fundamental particles and their antiparticles, constantly being created from energy and annihilating back into energy. As the universe expanded, it cooled. About 1 microsecond after the Big Bang, it had cooled enough for quarks to combine into protons and neutrons. These are the particles that would eventually form the nuclei of atoms, but they couldn't form those nuclei yet because it was still too hot. The matter-antimatter asymmetry became crucial in this moment. If matter and antimatter had been exactly equal, the protons would have all annihilated with antiprotons, the neutrons with antineutrons. But because there were slightly more matter particles than antimatter particles, when all the annihilation was done, a small fraction of matter particles remained. This is the matter that makes up everything we see. Every proton in every atom in your body, in the Earth, in the Sun, is a survivor from that era. It existed as one of the excess particles that didn't have an antiparticle partner to annihilate with.
About 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to stick together, forming the first atomic nuclei, mostly hydrogen and helium. These nuclei, born from the surviving matter particles, would later gather together under gravity to form the first stars. Those stars would create heavier elements in their cores, elements like carbon, nitrogen, oxygen, iron. When massive stars exploded as supernovas, they would scatter these elements through space, seeding the cosmos with the raw materials for planets, and eventually, life. All of this, the entire chain of events that led from the Big Bang to the universe we inhabit, depends on that initial matter-antimatter asymmetry. If the asymmetry hadn't existed, none of it would have happened. The universe would have ended up as a vast, empty expanse filled with nothing but light, photons carrying the energy that once was matter and antimatter before they mutually destroyed each other. Why this matters? You might wonder why scientists care so much about this problem. After all, the universe does exist. Matter is here. Does it really matter that we don't fully understand why? The answer is yes. It matters profoundly, for several reasons. First, understanding why the universe exists is one of the deepest questions humans can ask. It's not just scientific curiosity, it's a fundamental question about reality itself. Why is there something rather than nothing? The matter-antimatter asymmetry is the scientific form of this ancient philosophical question. Second, solving this mystery will almost certainly reveal new physics, new aspects of reality that we don't currently understand. Every time physics has confronted a major mystery like this, the resolution has led to revolutionary discoveries.
When we couldn't explain the orbit of Mercury, it led to general relativity. When we couldn't explain black-body radiation, it led to quantum mechanics.
This mystery about matter and antimatter is likely pointing us toward the next major revolution in our understanding. Third, the answer might connect to other deep mysteries in physics. Dark matter, the invisible substance that makes up most of the matter in the universe, is also unexplained by the Standard Model. Dark energy, the mysterious force accelerating the universe's expansion, is equally puzzling. These mysteries might be connected. Solving one might provide clues to solving the others. The search continues. Scientists are approaching this mystery from many directions simultaneously. In particle accelerators like the Large Hadron Collider, they're smashing particles together at enormous energies, trying to create conditions similar to the early universe and searching for new particles or processes that might explain the asymmetry. They're studying neutrinos with increasingly sophisticated detectors, looking for subtle asymmetries in how these particles behave. Neutrinos are peculiar particles that barely interact with anything, and they might hold clues to physics beyond the Standard Model. Cosmologists are examining the cosmic microwave background, the faint glow of light left over from the early universe, looking for patterns that might reveal what happened in those first moments. They're also studying the distribution of galaxies and the properties of dark matter, searching for connections to the matter-antimatter problem. Theorists are developing new mathematical frameworks, extending and modifying our current theories to incorporate the missing physics. Some of these ideas are elegant and beautiful, others are strange and counterintuitive. All of them are attempts to solve the puzzle of why anything exists. A gentle summary. Let's pause here and reflect on what we've explored so far. The universe began in a hot, dense state, and as it expanded and cooled, energy converted into particles.
According to the fundamental laws of physics, this should have created equal amounts of matter and antimatter. These particles should have found each other and annihilated, leaving nothing but energy behind. But that's not what happened. Instead, there was a tiny asymmetry, about one extra matter particle for every billion matter-antimatter pairs. When the annihilation was done, that small excess remained, and from it, everything we know emerged. Our current theories cannot fully explain this asymmetry. The Standard Model predicts some asymmetry, but not nearly enough. This failure tells us that there's physics we don't yet understand, new processes or particles that were active in the early universe. Understanding this mystery is one of the central goals of modern physics. It's not just about satisfying curiosity. It's about understanding why reality is the way it is, why there's a universe capable of giving rise to stars, planets, and life. The search for answers continues in laboratories and telescopes, in mathematical equations and computer simulations. We don't yet know what the answer will be, but we know that when we find it, it will transform our understanding of the universe. For now, rest in this mystery. The universe exists, and that existence is both miraculous and unexplained. Every atom in your body, every photon of light that reaches your eyes, every breath you take, exists because of a tiny, unexplained asymmetry that emerged in the first moments of time. In the next chapter, we'll explore the specific proposals scientists have made to explain this asymmetry. We'll look at the theories, the experiments, and the ongoing search for the physics that allowed the universe to exist. But for now, let this settle. The universe is a puzzle, and you are part of that puzzle, a piece of the mystery made manifest. Take a deep breath, rest in the wonder of existence, and when you're ready, we'll continue this gentle journey together.
Searching for the missing physics, where we begin again. Welcome back to this quiet exploration. In the first chapter, we established the central mystery, The universe exists when physics suggests it shouldn't. Matter dominates over antimatter, yet our best theories predict they should have been created in equal amounts and destroyed each other completely. Somewhere in the first moments of cosmic time, something happened that our current understanding cannot fully explain. Now, we'll explore the landscape of ideas that scientists have developed to solve this mystery. We'll look at the theories, the experiments, and the ongoing search for the missing piece of physics that allowed matter to survive. There's no urgency here, no race to a conclusion. We'll move through these ideas gently, letting each one unfold in its own time. Find your comfortable position again, let your mind settle, and we'll continue together, step by careful step, into the realm of physics beyond what we currently know. The landscape of possibilities. When faced with a mystery as profound as the matter-antimatter asymmetry, scientists don't pursue just one answer. Instead, they explore multiple possibilities simultaneously, developing different theories that each offer a potential solution. Some of these theories are extensions of what we already know, adding new elements to our current framework. Others are more radical, suggesting that we need to rethink fundamental aspects of reality. What unites all these approaches is that they attempt to satisfy Sakharov's three conditions we discussed earlier. They propose processes that violate baryon number conservation, that distinguish between matter and antimatter, and that occurred when the universe was out of thermal equilibrium. But each theory implements these conditions in different ways, invoking different particles, different forces, different mechanisms.
Let's explore these possibilities together, starting with some of the more conservative approaches and gradually moving toward more speculative ideas. Remember, none of these has been proven yet. They're all contenders, possibilities, waiting for evidence that might confirm or rule them out. Grand unified theories. One of the most elegant approaches to solving the matter-antimatter mystery involves what are called grand unified theories, or GUTs. These theories attempt to unify three of the four fundamental forces of nature into a single framework. In our current understanding, there are four fundamental forces. Gravity holds planets in orbit and keeps you anchored to the Earth. Electromagnetism governs how charged particles interact, giving rise to light, electricity, and magnetism. The strong nuclear force binds quarks together into protons and neutrons and holds atomic nuclei together despite the electromagnetic repulsion between protons. The weak nuclear force is responsible for certain types of radioactive decay and plays a crucial role in how stars shine. These forces seem very different from each other in our everyday experience. Gravity is weak but works over vast distances. Electromagnetism is stronger and also acts over long ranges. The strong force is incredibly powerful but only works over distances smaller than an atomic nucleus. The weak force is even more limited in range and seems to govern entirely different phenomena. But physicists have noticed patterns suggesting these forces might be different aspects of something more fundamental. In the 1960s and 70s, they successfully unified electromagnetism and the weak force into what's called the electro-weak force. At high enough energies, these two forces become indistinguishable, merging into a single force. Grand unified theories take this idea further, suggesting that at even higher energies, the electro-weak force and the strong force also merge.
At the enormous energies present in the first tiny fraction of a second after the Big Bang, all three forces would have been unified, different manifestations of a single underlying force. This unification has a beautiful consequence for the matter-antimatter problem. In GUTs, there are new particles called X and Y bosons that carry the unified force. These particles are extraordinarily heavy, far too massive to create in any particle accelerator we've built or could feasibly build. but in the extreme conditions of the very early universe, they would have existed. Here's the crucial point. When these X and Y bosons decay, they can violate baryon number conservation. They can create more quarks than antiquarks, or vice versa. They also violate CP symmetry, treating matter and antimatter differently. And they existed in the early universe when it was expanding rapidly out of thermal equilibrium. In other words, the decay of these hypothetical particles naturally satisfies all three of Sakharov's conditions. As the universe expanded and cooled, these heavy particles would have decayed, and their decay would have created a slight excess of matter over antimatter. When the universe cooled further and the remaining matter and antimatter annihilated, the small excess of matter would have survived. The numbers work out remarkably well. The asymmetry that guts predict is roughly the right size to explain what we observe. One extra matter particle for every 10 billion matter-antimatter pairs emerging from the decay of these exotic bosons in the first moments of cosmic time. The challenge of testing. Grand unified theories are beautiful and elegant, and they solve the matter-antimatter problem in a natural way. But they face a significant challenge. They're extremely difficult to test directly. The X and Y bosons, if they exist, are so massive that creating them would require energies far beyond what we can achieve in particle accelerators.
The Large Hadron Collider, the most powerful accelerator ever built, reaches energies of about 13 trillion electron volts. To create these hypothetical particles, we'd need energies about 1 trillion times higher. It's simply not feasible with any technology we can envision. However, guts make other predictions that we can potentially test. One of the most striking is that protons, the particles that make up most of the mass of ordinary matter, should not be absolutely stable. Given enough time, they should very occasionally decay. In our everyday experience, protons seem perfectly stable. An isolated proton will sit unchanged for as long as you care to watch it. But according to guts, this stability isn't absolute. Very rarely, perhaps once every 10 to the power of 34 years or so, a proton should decay into lighter particles. That's an almost unimaginably long time. The universe is only about 14 billion years old, which is about 10 to the power of 10 years. A proton's predicted lifetime in guts is about 1 trillion times longer than the current age of the universe. But here's the thing, if you watch enough protons for long enough, you might catch one decaying. Scientists have built massive detectors containing thousands of tons of water or other materials, which means they're watching an enormous number of protons simultaneously. These detectors sit deep underground, shielded from cosmic rays and other background radiation, waiting patiently to see if any proton will decay. So far, after decades of observation, no one has definitively observed proton decay. This null result has ruled out some versions of grand unified theories, those that predicted decay rates high enough that we should have seen events by now. But it hasn't ruled out all versions. More refined guts predict even longer proton lifetimes, beyond what current experiments can test. The search continues.
New detectors are being planned and built, larger and more sensitive than their predecessors. If proton decay is eventually observed, it would be revolutionary confirmation that grand unified theories are on the right track. If it continues to elude us, it will constrain these theories further, perhaps eventually ruling them out entirely. Leptogenesis, a different path. While grand unified theories focus on processes that directly create an excess of baryons, quarks of particles made from them, there's another elegant approach that takes a more indirect route. This approach is called leptogenesis, and it focuses on a different class of particles called leptons. Leptons include electrons, the particles that orbit atomic nuclei, and also neutrinos, those ghostly particles we mentioned earlier that barely interact with anything. The idea behind leptogenesis is that perhaps the universe first created an asymmetry in leptons, and then this lepton asymmetry was converted into the baryon asymmetry we observe. This might seem like adding an extra step, making the problem more complicated rather than simpler. But leptogenesis has some attractive features that make it worth considering seriously. The key players in leptogenesis are neutrinos. These particles are peculiar in many ways. They have almost no mass, far less than any other particle with mass that we know of. They barely interact with other matter, passing through the Earth or even the Sun as if nothing were there. Trillions of neutrinos from the Sun pass through your body every second, and you never notice, because they almost never interact with your atoms. In the Standard Model, neutrinos are unusual in another way. They're the only fundamental particles that don't have right-handed versions. This is a bit technical, but particles can spin in different ways, and we describe these different spinning states as left-handed or right-handed.
Most particles come in both versions, but in the Standard Model, neutrinos only come in the left-handed variety. This is strange, and many physicists suspect it's a sign that the Standard Model is incomplete when it comes to neutrinos. Perhaps right-handed neutrinos do exist, but they interact so weakly with everything else that we haven't detected them yet. These hypothetical right-handed neutrinos are sometimes called sterile neutrinos because they don't participate in any of the Standard Model forces except gravity. In leptogenesis scenarios, these sterile neutrinos are the key. Imagine that in the early universe, very heavy sterile neutrinos existed. Like the X and Y bosons in grand unified theories, these particles would have been too massive to create in modern particle accelerators, but they could have existed in the hot, dense conditions right after the Big Bang. When these heavy sterile neutrinos decayed, they would have violated lepton number conservation and CP symmetry. Their decay would have created slightly more leptons than antileptons, establishing an asymmetry in the lepton population. Now here's where it gets interesting. There's a process in particle physics, allowed even in the Standard Model, that can convert leptons into baryons. It's called a sphaleron process, and was active in the early universe when temperatures were high enough. These sphaleron processes would have taken the lepton asymmetry and partially converted it into a baryon asymmetry. The result is the same as in grand unified theories, a small excess of matter over antimatter. But the path to that result is different, involving neutrinos rather than exotic bosons carrying a unified force. The appeal of leptogenesis. Leptogenesis is attractive for several reasons. First, we already know that neutrinos are weird. We know they have mass, even though the original Standard Model predicted they should be massless.
We know their masses are extraordinarily tiny compared to other particles for reasons we don't fully understand. The existence of heavy sterile neutrinos would help explain some of these mysteries. Second, leptogenesis connects to other problems in physics. Those hypothetical heavy sterile neutrinos could also be related to dark matter, the invisible substance that makes up most of the matter in the universe. Or they could connect to mechanisms that explain why neutrino masses are so small compared to other particles. Third, leptogenesis makes predictions that we might be able to test. The light neutrinos we've already detected should have certain properties if leptogenesis is correct. Experiments studying neutrinos in detail, measuring their masses and how they oscillate between different types, might provide evidence for or against this scenario. Several large neutrino experiments are currently running or under construction. They're studying neutrinos from nuclear reactors, from particle accelerators, from the atmosphere, and from the sun. These experiments are measuring neutrino properties with increasing precision, and their results will help determine whether leptogenesis is viable. Electroweak baryogenesis, working with what we know. Both grand unified theories and leptogenesis invoke new physics, particles that we haven't directly detected. But there's another approach that tries to generate the matter-antimatter asymmetry using only the particles and forces we already know about, with minimal additions. This approach is called electroweak baryogenesis, and it focuses on a moment in the early universe called the electroweak phase transition. Remember how we mentioned that electromagnetism and the weak force are unified at high energies? In the very early universe, when temperatures were extremely high, these two forces were indeed unified as a single electroweak force. But as the universe expanded and cooled, it underwent a phase transition, similar to how water freezes into ice, and the electroweak force split into the separate electromagnetic and weak forces we see today. This phase transition occurred when the universe was about a billionth of a second old, at a temperature of about 1 trillion degrees. During this transition, the Higgs field, which gives particles their mass, underwent a dramatic change throughout the universe. In electroweak baryogenesis scenarios, the matter-antimatter asymmetry is generated during this phase transition. The idea is that as the Higgs field changed, it created conditions where baryon number violation could occur, and where the universe was out of thermal equilibrium. Combined with CP violation, which we know exists in the Standard Model, all three Sakharov conditions could be satisfied. The appealing aspect of this scenario is that it doesn't require exotic, undetected particles. The Higgs boson has been discovered. We found it at the Large Hadron Collider in 2012. The electroweak phase transition definitely happened. We can see its effects in the structure of the universe today. And we know CP violation exists in the Standard Model from observations of particle decays. So all the ingredients are there, in principle. The question is whether they're sufficient to produce the observed matter-antimatter asymmetry, the challenge for electroweak baryogenesis. Unfortunately, when physicists calculate the asymmetry that electroweak baryogenesis can produce using only Standard Model physics, they find it's not enough. The CP violation in the Standard Model is too weak, and the electroweak phase transition isn't strong enough to keep the universe sufficiently out of equilibrium. But this doesn't kill the idea entirely. It just means we need to add something to the Standard Model, some modification or extension that strengthens the CP violation or makes the phase transition more dramatic.
One popular addition is extra Higgs bosons beyond the single one we have discovered. In the Standard Model, there's just one Higgs particle, but in extensions like supersymmetry, which we'll discuss shortly, there are multiple Higgs particles. These additional Higgs bosons could strengthen the phase transition and provide additional sources of CP violation. Another possibility is that the Higgs boson we discovered isn't exactly the Standard Model Higgs. Perhaps it has additional properties or interactions that we haven't detected yet. Physicists are studying the Higgs boson in great detail at the Large Hadron Collider, measuring how it decays and how it interacts with other particles, looking for any deviation from Standard Model predictions. So far, the Higgs looks very much like the Standard Model predicts, but the measurements aren't yet precise enough to rule out small deviations. Future colliders, more powerful than the LHC, might be able to detect these subtle differences if they exist. Electroweak baryogenesis remains an active area of research precisely because it connects to things we can test right now. Unlike grand unified theories or leptogenesis, which invoke particles far too heavy to create directly, electroweak baryogenesis deals with energy scales we can probe in particle accelerators. If it's the right explanation, we should be able to find evidence for it in our experiments. Supersymmetry and the matter-antimatter problem. Let's talk about supersymmetry, one of the most discussed extensions of the Standard Model. Supersymmetry, often abbreviated as SUSY, is a proposed symmetry between two types of particles, fermions and bosons. Fermions are particles like electrons, quarks, and neutrinos. They make up matter. Bosons are force-carrying particles like photons, gluons, and the W and Z bosons. In supersymmetry, every fermion has a boson partner, and every boson has a fermion partner.
This might sound like arbitrary complication, but supersymmetry solves several problems in physics. It helps with the hierarchy problem, explaining why gravity is so much weaker than the other forces. It provides candidates for dark matter particles, And it's a necessary ingredient in string theory, a candidate for a theory of everything. Supersymmetry also has implications for the matter-antimatter asymmetry. The supersymmetric partners of known particles could provide new sources of CP violation beyond what exists in the standard model. They could strengthen the electroweak phase transition, making electroweak baryogenesis viable, or they could participate in leptogenesis or other mechanisms for generating the asymmetry. The challenge is that despite decades of searching, we haven't found any supersymmetric particles. The Large Hadron Collider has been looking for them intensively, and so far they haven't appeared. This doesn't mean supersymmetry is wrong necessarily. It might just mean that the supersymmetric particles are heavier than we can currently produce, or that they interact too weakly for us to detect easily. But the continued absence of supersymmetric particles is making physicists reconsider. Some versions of supersymmetry are being ruled out by the LHC's null results. The parameter space, the range of possibilities for what supersymmetry might look like, is shrinking. Still, supersymmetry remains an active research area, and its potential role in generating the matter-antimatter asymmetry continues to be explored. If supersymmetric particles are eventually discovered, it would revolutionize physics and potentially solve multiple mysteries at once, including the one we're exploring: the role of the Higgs field. Let's delve a bit deeper into the Higgs field, because it plays a central role in several scenarios for matter-antimatter asymmetry, particularly in electroweak baryogenesis. The Higgs field is a field that permeates all of space.
It's always there, everywhere. Even in the vacuum of empty space, particles acquire mass by interacting with this field. The stronger a particle's interaction with the Higgs field, the more massive the particle is. Photons don't interact with the Higgs field at all, which is why they're massless and travel at the speed of light. In the very early universe, the Higgs field was in what's called a symmetric state. It was effectively zero everywhere, and particles didn't have mass in the way they do today. As the universe cooled, the Higgs field underwent a phase transition, settling into a non-zero value throughout space. This is called symmetry breaking, and it's when particles acquired their masses. This phase transition is crucial for electroweak baryogenesis. The idea is that the transition didn't happen uniformly everywhere at once. Instead, bubbles of the new phase, where the Higgs field had a non-zero value, formed and expanded, eventually filling all of space. At the walls of these expanding bubbles, conditions would have been right for generating a matter-antimatter asymmetry. The physics inside the bubble would have been different from outside, creating a situation out of thermal equilibrium. Particles interacting with the moving bubble wall could have their baryon number changed, and CP violation could have created a preference for matter over antimatter. As the bubbles expanded and merged, they would have trapped this asymmetry inside them. The matter excess generated at the bubble walls would have been locked in, unable to equilibrate away. And this excess, summed up over all the bubbles forming throughout the universe, would have become the net matter-antimatter asymmetry we observe. This is an elegant picture, but it requires the phase transition to be what's called strongly first order. The transition needs to happen abruptly, with distinct phases separated by well-defined bubble walls.
In the standard model, calculations suggest the transition was more gradual, not abrupt enough for this mechanism to work efficiently. This is why extensions to the standard model are needed. Additional Higgs bosons or other new physics could make the phase transition stronger, creating the conditions necessary for electroweak baryogenesis to succeed. Cosmic strings and topological defects. Here's a more exotic possibility. Perhaps the matter-antimatter asymmetry was generated by topological defects in the structure of space-time itself. When the universe undergoes phase transitions, like the electroweak phase transition we just discussed, or other transitions at even earlier times, it can form defects. These are regions where the fields couldn't settle into their new states smoothly everywhere, creating structures like cosmic strings, domain walls, or monopoles. Think of it like when water freezes. If it freezes quickly and unevenly, you can get cracks and irregularities in the ice. Similarly, when the universe underwent phase transitions, it might have formed irregularities in the field configurations. Cosmic strings are particularly interesting. They're thin, one-dimensional structures, like infinitely long strings of concentrated energy threading through space. They're predicted by many theories of physics beyond the Standard Model, though they've never been directly observed. These cosmic strings could have played a role in generating the matter-antimatter asymmetry. As they formed and evolved in the early universe, they could have created regions where baryon number was violated, where CP symmetry was broken, and where the universe was out of equilibrium. The interactions of particles with these cosmic strings could have generated local excesses of matter over antimatter. This scenario is speculative, more so than the others we've discussed. It requires not just new particles, but new large-scale structures in the early universe.
And it's harder to test, because cosmic strings, if they exist, would have diluted away as the universe expanded, leaving at most faint traces in the cosmic microwave background or in the distribution of galaxies. Still, it's a possibility that physicists consider. The universe's phase transitions in its early moments were complex events, and they might have involved dynamics we don't yet fully understand. Topological defects are a natural consequence of such transitions in many theories, and exploring their potential role in baryogenesis is part of the broader search for answers. Asymmetric dark matter. So far, we've been focusing on explaining the asymmetry of ordinary matter, the baryons and leptons that make up atoms and everything we can directly observe. But there's another mystery lurking in the background: dark matter. Dark matter is invisible material that doesn't emit, absorb, or reflect light. We know it exists because of its gravitational effects. Galaxies rotate in ways that only make sense if they contain much more mass than we can see. Galaxy clusters are held together by gravity that requires more mass than their visible matter can provide. The cosmic microwave background shows patterns that indicate dark matter was present in the early universe. Yet we don't know what dark matter is made of. It's not made of ordinary atoms. It must be some new type of particle, beyond the Standard Model, that doesn't interact with light or with the strong nuclear force, but does interact gravitationally and possibly through other weak forces. Here's an interesting observation. The amount of dark matter in the universe is roughly 5 times the amount of ordinary matter. That's a curious ratio. It's not a huge factor like 1,000,000 or 1,000,000,000, it's just about 5. This similarity in scale has led some physicists to wonder whether there might be a connection. What if dark matter also has an asymmetry, similar to the matter-antimatter asymmetry of ordinary matter?
What if dark matter particles slightly outnumber dark antimatter particles, and this asymmetry was generated by the same mechanism that created the ordinary matter asymmetry? This is the idea behind asymmetric dark matter models. In these scenarios, there's a connection between the dark sector and the ordinary matter sector. Perhaps they're linked through some common physics in the early universe, some process that generated both asymmetries simultaneously. If this is right, it would explain the curious 5-to-1 ratio. The mechanisms that determine the matter-antimatter asymmetry would also determine the dark matter-dark antimatter asymmetry, and the ratio between them would emerge from the details of the physics, not as a coincidence, but as a necessary consequence. Asymmetric dark matter models make predictions that might be testable. For instance, they suggest that dark matter particles might interact with ordinary matter through forces other than just gravity. Experiments searching for dark matter directly by looking for dark matter particles colliding with detector atoms deep underground might find evidence for these interactions. So far, these searches haven't yielded definitive detections, but they're ongoing and improving. If dark matter is eventually discovered and characterized, and if it turns out to have properties consistent with asymmetric dark matter models,
it would be a beautiful unification of two major mysteries in physics, the inflaton and reheating. Let's shift our perspective to an even earlier moment in cosmic history. Before the universe was 1 second old, before it was a billionth of a second old, there was likely a period called cosmic inflation. Inflation is a theory that the universe underwent a brief period of extremely rapid expansion in its first moments, growing from subatomic size to macroscopic size in a tiny fraction of a second.
This rapid expansion solves several problems in cosmology, explaining why the universe is so uniform on large scales and why it's geometrically flat. Inflation is driven by a field called the inflaton, similar to how the Higgs field we discussed earlier is a field permeating space. During inflation, the inflaton field dominated the universe's energy, driving the rapid expansion. Eventually, inflation ended. The inflaton field decayed, converting its energy into particles, filling the universe with the hot soup of matter and radiation that we described in Chapter 1. This process is called reheating because it heats the universe back up after the cold expansion of inflation. Here is the interesting part for our purposes. The reheating process might have been when the matter-antimatter asymmetry was generated. As the inflaton field decayed into particles, it could have done so in a way that violated baryon number, distinguished between matter and antimatter, and occurred out of thermal equilibrium. This scenario is called Affleck-Dine baryogenesis, named after the physicists who first proposed it. It involves additional fields beyond the inflaton, fields that carry baryon number or lepton number, and that interact with the inflaton during reheating. The details are technical, but the basic idea is elegant. The very process that filled the universe with matter and energy after inflation could also have been the process that created the matter-antimatter asymmetry. It would mean that baryogenesis and reheating are intimately connected, two aspects of the same cosmic event. Testing this scenario is challenging because it involves physics at extremely high energies, even higher than the electroweak scale. But it makes predictions about inflation itself, about the properties of the inflaton field and how reheating occurred.
As our observations of the cosmic microwave background become more precise, and as our understanding of inflation improves, we might be able to test aspects of this scenario indirectly. Spontaneous baryogenesis. Here's yet another approach, one that's quite different from the others. What if the matter-antimatter asymmetry wasn't generated by particle decays or phase transitions, but by the expansion of the universe itself? This idea, called spontaneous baryogenesis, suggests that baryon number violation can occur when space-time itself is changing, when the universe is expanding. The expansion creates a kind of current in baryon number, a flow that generates an asymmetry even without specific particle processes. It's a bit like how a river flowing downhill generates motion in objects floating on it. The objects don't need any internal mechanism to start moving. The flow of the river itself carries them along. Similarly, in spontaneous baryogenesis, the expansion of the universe creates a flow in baryon number. This requires a connection between the expansion of spacetime and baryon number, which isn't present in the standard model. You need a field that couples to both the geometry of spacetime and to baryon number. But if such a field exists, it provides a very general mechanism for baryogenesis that doesn't depend on the specific details of particle physics. Spontaneous baryogenesis is elegant in its generality, but it's also harder to test precisely because it's so general. It doesn't make specific predictions about particle masses or decay rates that we could look for in accelerators. Instead, it would require detecting the field that couples to baryon number and spacetime curvature, which is challenging. Still, it's a reminder that there are many possible solutions to the matter-antimatter problem. coming from different perspectives and making different assumptions about how physics works. The experimental search. All these theories are interesting intellectually, but physics is ultimately an experimental science. Theories must make predictions that can be tested, and experiments must search for the evidence that will confirm or rule them out. The search for the physics behind the matter-antimatter asymmetry is happening on many fronts simultaneously. Let's walk through some of the key experimental efforts, understanding what they're looking for and how they might solve the mystery. First, there are the particle accelerators, with the Large Hadron Collider being the most powerful currently operating. These machines smash particles together at high energies, recreating conditions similar to the early universe, and searching for new particles or new interactions. The LHC is looking for many things relevant to our mystery. It's searching for supersymmetrical particles that could provide new sources of CP violation. It's measuring the properties of the Higgs boson in detail, looking for signs of additional Higgs particles or unexpected interactions. It's studying how quarks and mesons decay, searching for new sources of matter-antimatter asymmetry beyond what the standard model predicts. Every collision at the LHC produces a shower of particles that detectors record. Physicists analyze these collisions, billions of them, looking for rare events that might indicate new physics. It's like searching for a handful of unusual grains in a vast beach of sand, but the search is methodical and precise. So far, the LHC hasn't found definitive evidence for physics beyond the standard model related to baryogenesis, but it has ruled out many possibilities, constraining the theories and narrowing the search space. This is valuable progress, even if it hasn't yet provided the breakthrough we're hoping for. Future colliders are being planned that would reach even higher energies or study certain processes in more detail.
The International Linear Collider, the Compact Linear Collider, and a potential future circular collider are all under discussion. These machines might be able to probe energy scales and processes that the LHC cannot reach. Neutrino experiments. Neutrino physics is another crucial frontier. As we discussed, neutrinos might hold the key to leptogenesis, and understanding their properties in detail is essential for testing these scenarios. Neutrino experiments come in many varieties. Some use neutrinos from nuclear reactors, studying how they change as they travel from the reactor to the detector. Others use neutrino beams from particle accelerators, shooting neutrinos through the Earth to detectors hundreds of miles away. Still others study neutrinos from natural sources, like the atmosphere or the sun. One of the key questions these experiments are addressing is whether neutrinos are their own antiparticles. Most particles are distinct from their antiparticles, but neutrinos might be special, identical to their antiparticles. If they are, it would have profound implications for leptogenesis and for our understanding of why neutrino masses are so small. This property, being your own antiparticle, allows a process called neutrino-less double beta decay. Some atomic nuclei could, very rarely, undergo a decay process that emits 2 electrons but no neutrinos. Observing this process would prove that neutrinos are their own antiparticles and would provide crucial information about neutrino masses. Experiments searching for neutrino-less double beta decay are among the most sensitive in all of physics. They use ultra-pure materials, shielded deep underground from cosmic rays, cooled to extremely low temperatures, watched continuously for years. They're looking for an event that might happen once in a billion years in any individual nucleus, but by watching enormous numbers of nuclei, they hope to catch it.
If neutrinoless double beta decay is observed, and if the rate is measured, it would tell us about neutrino masses and potentially confirm aspects of leptogenesis scenarios. It would be a major breakthrough in understanding both neutrinos and the matter-antimatter asymmetry. Precision measurements of CP violation. Another experimental approach is to measure CP violation with increasing precision in various particle processes.
We know CP violation exists in the decays of certain mesons. By measuring exactly how much CP violation occurs and in which processes, we can test whether the standard model's predictions are accurate or whether there are additional sources of CP violation. Experiments at facilities like Keck in Japan and CERN in Europe are studying B mesons and D mesons, particles containing bottom quarks and charm quarks, respectively. These particles decay in various ways, and by comparing the decay rates of particles and antiparticles, physicists can measure CP violation. So far, the standard model's predictions for CP violation have held up well in most tests, but there are hints, not yet definitive, of potential discrepancies in some measurements. These could be statistical fluctuations, or they could be the first signs of new physics. More data is being collected continuously. As the statistics improve and measurements become more precise, any real deviations from the standard model should become clearer. If additional sources of CP violation are found, it would point toward specific extensions of the standard model and guide theoretical work on baryogenesis. Cosmological observations. Not all the evidence will come from particle accelerators or underground detectors. Cosmology, the study of the universe as a whole, also provides crucial tests. The cosmic microwave background, the afterglow of the Big Bang, contains information about the early universe.
Tiny temperature variations in this radiation tell us about density fluctuations in the early universe, about the amount of ordinary matter and dark matter, about the expansion rate and geometry of space. Future observations might detect gravitational waves from the early universe, ripples in space-time produced during cosmic inflation or phase transitions. These could provide information about what happened in the first moments of cosmic time, potentially revealing the conditions when baryogenesis occurred. The distribution of matter in the universe today, the patterns of galaxies and clusters, also encodes information about the early universe. As we map the cosmos in more detail, we might find signatures of the processes that generated the matter-antimatter asymmetry. The interplay of theory and experiment. Science progresses through an ongoing conversation between theory and experiment. Theorists propose ideas about how the universe might work, making predictions that can be tested. Experimentalists design and conduct experiments to test these predictions. The results inform new theories, which make new predictions, leading to new experiments, in an ever-advancing cycle. For the matter-antimatter mystery, this cycle is in full swing. We have multiple theoretical frameworks, each making different predictions. We have numerous experiments underway, each probing different aspects of the problem. As results come in, some theories are ruled out, others are refined, and new ones are proposed. This process can seem slow, especially for those waiting for a definitive answer. Decades have passed since the problem was first clearly articulated, and we still don't have a confirmed solution. But this is the nature of fundamental physics.
The questions are deep. The phenomena we're studying occurred in extreme conditions we can barely recreate, and patience is essential. Progress is happening, even if it's gradual. The parameter space of possible solutions is being mapped out systematically. We know more now than we did a decade ago about what baryogenesis is not, which theories don't work, which energy scales don't contain the answer. This negative knowledge is valuable. It guides us toward where the answer must lie. The role of serendipity. It's worth noting that sometimes the breakthrough comes from an unexpected direction. The history of physics is filled with examples of discoveries that nobody anticipated, observations that didn't fit into any existing framework and forced a complete rethinking of our understanding. The cosmic microwave background was discovered accidentally by engineers trying to eliminate noise from a radio antenna. The acceleration of the universe's expansion, implying dark energy, was a complete surprise to cosmologists. The discovery that neutrinos have mass contradicted the standard model's predictions.
Perhaps the solution to the matter-antimatter mystery will come from a similarly unexpected observation. A detector designed to study something else entirely might stumble upon a phenomenon that reveals the missing physics. An astronomical observation might show a pattern that theorists hadn't considered. This is why broad experimental programs are important. We can't predict exactly where the answer will come from, so we need to be looking in many places, studying many phenomena, ready to recognize the unexpected when it appears. Theoretical challenges. While experiments search for evidence, theorists face their own challenges. Creating a theory that explains the matter-antimatter asymmetry isn't just about satisfying Sakharov's three conditions. The theory must also be consistent with everything else we know about physics.
It must not contradict the successful predictions of the Standard Model. It must not violate conservation laws that we know hold to high precision. It must be mathematically consistent, free of internal contradictions or anomalies. And ideally, it should explain other mysteries as well, not just baryogenesis, but also dark matter, dark energy, neutrino masses, and other unsolved problems. This is a tall order. It's easy to write down a theory that explains one thing but breaks something else. Finding a theory that fits all the constraints while remaining testable is extremely difficult. Moreover, theorists must work with limited guidance from experiment. Unlike in earlier eras of physics, where experiments were regularly finding new particles and phenomena that theories had to explain, the recent decades have seen fewer experimental surprises. The LHC confirmed the Higgs boson, which was predicted, but hasn't found the supersymmetric particles or other new physics that many theories predicted. This means theorists are working somewhat in the dark, exploring possibilities without clear experimental signposts pointing the way. It requires creativity, mathematical skill, and the willingness to pursue ideas that might turn out to be wrong. The sociology of physics. There's also a human element to this search. Physics isn't done by isolated individuals. It's a community effort, with thousands of researchers around the world working on related problems, sharing results, debating interpretations. Different research groups pursue different approaches. Some focus on grand unified theories, others on leptogenesis, still others on electroweak baryogenesis or more exotic scenarios. This diversity is healthy. It ensures that multiple possibilities are explored in parallel. But it also means that the community must work together to synthesize results, to understand how different pieces of evidence fit together. Conferences and workshops bring researchers together to share findings.
Papers are published and peer-reviewed, subjecting ideas to critical scrutiny. Graduate students and postdocs move between institutions, spreading knowledge and perspectives. The culture of physics values both boldness and rigor. Researchers are encouraged to propose creative new ideas, but they're also expected to test those ideas critically, to look for flaws, to compare predictions with data. It's a balance between imagination and discipline. Where we stand now. Let's pause and take stock of where we are in this search. We've explored multiple theoretical frameworks for explaining the matter-antimatter asymmetry, grand unified theories, leptogenesis, electroweak baryogenesis, supersymmetry, inflaton decay, spontaneous baryogenesis, asymmetric dark matter. Each has its appeals and its challenges. We've discussed the experimental efforts, particle accelerators searching for new particles and interactions, neutrino experiments measuring fundamental properties, precision measurements of CP violation, cosmological observations of the early universe. Each is pushing the boundaries of what we can measure and observe. But we don't yet have a definitive answer. We don't know which, if any, of these theoretical frameworks is correct. We haven't found the missing physics that explains why matter dominates over antimatter. This might seem disappointing, but it's important to remember how profound the question is. We're asking why the universe exists, why there's something rather than nothing. This is among the deepest questions humans can pose, and it would be surprising if the answer came easily. The search continues. New experiments are being planned and built. New theoretical ideas are being developed and tested. Slowly, methodically,
The community is working toward an answer. The patience of science. Science requires patience.
It requires the willingness to pursue questions for decades, to build on the work of previous generations, to contribute pieces to a puzzle that might not be completed in one's lifetime. The matter-antimatter mystery has been under investigation for over half a century now, since Sakharov first articulated the conditions for baryogenesis in 1967. Many physicists have devoted their careers to aspects of this problem. Some have proposed theories that have since been ruled out. Others have built experiments that haven't yet found what they're searching for. But each effort contributes. Each ruled-out theory narrows the possibilities. Each null result from an experiment constrains the parameter space. The progress is real, even when it doesn't come in the form of dramatic breakthroughs. And there's value in the search itself, beyond just finding the answer. The experiments built to search for proton decay or neutrinoless double beta decay have pushed technological boundaries, developing detectors and techniques that have applications beyond their original purpose. The theoretical work on baryogenesis has deepened our understanding of particle physics, cosmology, and the connections between them. Students trained in these research programs go on to apply their skills in many areas. The culture of rigorous inquiry, of testing ideas against evidence, of working collaboratively on difficult problems, these skills and approaches have value throughout science and society. The wonder of not knowing. There's something profound about living in a time when fundamental questions remain open. We are privileged to exist in an era when we can ask why the universe exists and know that we don't yet have a complete answer, but that the answer is within reach if we keep searching. A few centuries ago, these questions wouldn't have been formulated in the way we understand them now. The very concepts of matter and antimatter, of particle physics and cosmology, didn't exist.
Humans wondered about creation and existence, but in mythological or philosophical terms, not in terms that could be tested experimentally. A few centuries from now, if humanity continues to advance, these questions might be settled. Future scientists might look back on our era as the time when the matter-antimatter mystery was solved, when the missing physics was finally discovered. They might wonder what it was like to not know, to work in the fog of uncertainty. We are in that fog now, and there's a certain beauty to it. The uncertainty means the answer is still out there, waiting to be found. Every experiment might be the one that reveals it. Every theoretical insight might be the key that unlocks the mystery. A gentle reflection. Rest here for a moment in this landscape of possibilities. We've walked through multiple theories, each attempting to explain why the universe exists. We've seen how experiments are searching for evidence, how theorists are constructing frameworks, how the community is working collectively toward understanding. None of this is certain yet. The universe guards its deepest secrets carefully, revealing them only to those who search with patience and precision. But the search itself is meaningful. It represents humanity's ongoing quest to understand reality, to look deeper into the nature of existence. You are part of this cosmic story. The atoms in your body are survivors from the first moments of time, matter particles that escaped annihilation because of a mysterious asymmetry we're still trying to understand. You exist because of this unexplained imbalance, and your curiosity about it is the universe attempting to understand itself. Breathe slowly. Let these ideas settle. The matter-antimatter mystery remains open, a question mark at the heart of existence. But it's a question we're actively pursuing, with tools and theories and dedication. The answer is out there, waiting.
In our final chapter, we'll explore what might happen when we find that answer, how it might change our understanding of the universe,
and what new questions it might open up. But for now, rest in the knowledge that the search continues, that thousands of people around the world are working toward understanding why anything exists at all. Take your time. Let your mind wander through these possibilities, and when you're ready, we'll move forward together into the final part of this gentle exploration, the future of understanding, returning to the mystery. Welcome to the final part of our journey together. We've traveled through the foundations of the mystery, why the universe exists when physics suggests it shouldn't, and explored the many theories scientists have proposed to solve it. Now we'll look forward, imagining what might happen when the answer is finally found, and how that discovery might reshape our understanding of reality itself. Find your place of comfort once more. Let your breathing slow and deepen. This final chapter is about possibilities, about futures both near and distant, about what it means to seek answers to the deepest questions we can ask. The moment of discovery. Imagine for a moment the day when the matter-antimatter mystery is finally solved. It might happen in a laboratory when a detector deep underground registers an event that shouldn't occur according to the standard model. Perhaps a proton decay, witnessed after decades of patient watching, confirming that grand unified theories are correct. Or perhaps neutrinoless double beta decay, revealing that neutrinos are their own antiparticles and pointing toward leptogenesis as the answer. Or maybe the breakthrough will come from a particle accelerator. A new particle might appear in the debris of a high-energy collision, a particle predicted by supersymmetry or some other extension of the standard model. Its properties, carefully measured, might reveal the missing source of CP violation needed to explain the matter-antimatter asymmetry. The discovery might come from cosmology instead. Observations of the cosmic microwave background or gravitational waves from the early universe might reveal signatures of the phase transitions or processes that generated the asymmetry. Patterns in the distribution of galaxies might encode information about the physics of the first moments of cosmic time. However it happens, the discovery won't be a single dramatic moment, despite how it might be portrayed in news headlines. Science rarely works that way. Instead, it will likely be a gradual accumulation of evidence, multiple experiments pointing in the same direction, a growing consensus that a particular theory is correct. First will come hints, results that suggest something interesting but aren't yet conclusive. These hints will motivate more experiments, more detailed studies. Slowly, the evidence will build. Alternative explanations will be ruled out one by one. The error bars on measurements will shrink, and eventually the community will reach the point where the conclusion is unavoidable. We understand why the universe exists. The immediate impact. When that moment comes, the impact will be profound. First, within physics itself. Confirming the mechanism of baryogenesis will validate whichever extension of the standard model turns out to be correct. If it's grand unified theories, we'll know that the fundamental forces really do unify at high energies. If it's leptogenesis, we'll have learned crucial facts about neutrinos and the existence of new particles. If it's electroweak baryogenesis with supersymmetry, we'll have discovered a whole new layer of particles underlying the ones we know. This confirmation will guide future research. Knowing which framework is correct tells physicists where to look next, what experiments to build, what calculations to perform.
It will open new questions even as it answers the old one. For instance, if grand unified theories are confirmed, physicists will want to understand the unified force in detail, to predict its properties precisely, to search for other consequences of unification. They'll want to understand how the unified force splits into the separate forces we see today, what determines the strengths of each force,
why quarks and leptons have the masses they do. If leptogenesis is the answer, it will raise questions about the sterile neutrinos that must exist. How many types are there? What are their masses? How do they interact with ordinary matter? Could some of them be dark matter? The search for these particles will become a major focus of experimental physics. Understanding baryogenesis might also connect to other mysteries: dark matter, dark energy, the masses of neutrinos, the hierarchy of particle masses, the strong CP problem. These and other puzzles might find their solutions in the same framework that explains the matter-antimatter asymmetry. Solving one mystery often illuminates others. Technological ripples. The discovery will have technological consequences as well, though perhaps not immediately. Understanding fundamental physics has always, eventually, led to practical applications, even when those applications weren't foreseeable at the time of discovery. Quantum mechanics, developed to understand atoms, now underlies all of electronics, from computer chips to lasers to medical imaging. General relativity, Einstein's theory of gravity, is essential for the GPS satellites that guide navigation. Nuclear physics enables both power generation and medical treatments. We can't predict exactly what technologies will emerge from understanding baryogenesis, but we can be confident that they will emerge. The experiments built to solve this mystery are already pushing technological boundaries.
Detectors sensitive enough to catch a single particle decay, accelerators that reach ever higher energies, computational methods to analyze enormous data sets. All of these have applications beyond their immediate purpose. Moreover, confirming physics beyond the standard model means there are new forces, new particles, new phenomena to work with. History suggests that whenever humans gain access to new physical phenomena, they eventually find ways to use them. Perhaps we'll learn to manipulate the Higgs field in ways that affect how particles acquire mass. Perhaps we'll discover new types of radiation or particles that can be used for imaging or communication. Perhaps understanding the unified forces will suggest new energy sources or new materials. These are speculations, of course, but the pattern is clear. Fundamental understanding leads to practical application, given time. Philosophical implications. Beyond physics and technology, solving the matter-antimatter mystery will have philosophical implications. It will change how we think about existence itself. For thousands of years, humans have asked why there is something rather than nothing. Philosophers and theologians have proposed countless answers, from divine creation to logical necessity to pure chance. The scientific answer, when it comes, will be different from all of these. It will be precise, mathematical, testable. It will say, the universe exists because of these specific processes, governed by these specific laws, occurring in these specific conditions in the first moments of cosmic time. This doesn't diminish the question's profundity. If anything, it deepens it. We'll understand the mechanism of existence, but that understanding will raise new questions. Why do these laws exist? Why these particular values for the fundamental constants? Why is the universe governed by mathematics at all? Science pushes the mystery back, but doesn't eliminate it. Each answer reveals new depths to explore.
Understanding baryogenesis will tell us how the universe populated itself with matter, but it won't explain why the universe began in the first place, why the laws of physics are what they are, why there's a reality for those laws to govern. These deeper questions might remain forever beyond scientific inquiry. Or perhaps they too will eventually yield to sufficiently clever theoretical and experimental work. We don't know yet, and that uncertainty is part of what makes the quest meaningful. Educational transformation. When the matter-antimatter mystery is solved, it will change how we teach physics. Future textbooks will include the solution, presenting it alongside the Standard Model and general relativity as part of our established understanding of nature. Students will learn about the early universe not as a realm of speculation, but as a domain we understand in detail. They'll study the specific processes that generated the matter-antimatter asymmetry, work through the mathematics that describes it, see how the theory connects to experimental evidence. This will reshape what it means to study physics. Today's students are learning a theory, the Standard Model, that we know is incomplete. They're taught to think about its limitations, to wonder what lies beyond it. Future students will learn a more complete picture, one that explains not just how particles behave now, but why particles exist at all. But this change will also preserve the spirit of inquiry. Even with baryogenesis understood, there will be mysteries remaining. Students will still be encouraged to question, to wonder, to imagine what we don't yet know. The frontier will have moved, but it won't have disappeared. A new generation of questions. Indeed, solving the matter-antimatter mystery will open up entirely new questions, some of which we can barely imagine now. This is always how science advances. Each answer is also a beginning.
If we confirm that protons decay, we'll want to measure their lifetime precisely, understand exactly which decay channels are possible, test whether all the predicted decays actually occur. This will require experiments even larger and more sensitive than the ones running today, detectors containing hundreds of thousands of tons of material, watched for decades. If we discover supersymmetric particles, we'll want to map out the entire spectrum of supersymmetry, finding all the partner particles, measuring their masses and interactions. This will require new accelerators, more powerful than the Large Hadron Collider, capable of producing the heaviest supersymmetric particles. If we confirm the existence of heavy sterile neutrinos involved in leptogenesis, we'll want to understand their properties in detail. Are there 3 types, mirroring the 3 types of ordinary neutrinos? Or are there more? What are their masses? Do they interact through any forces beyond gravity? Could some of them account for dark matter? Each of these questions represents years or decades of future research. Solving baryogenesis won't end the field of particle physics and cosmology. It will revitalize it, providing clear targets for the next generation of experiments and theories. The grand unified picture. Let's imagine what our understanding might look like once baryogenesis is solved and we've followed some of the threads it reveals. We might have a grand unified theory that describes how all the forces merge at high energies. We might understand the complete spectrum of particles, including all the supersymmetric partners or other beyond standard model particles. We might know in detail what happened in the first second of the universe's existence.
We could trace the evolution from the end of inflation through the various phase transitions, including the one that generated the matter-antimatter asymmetry, through the formation of the first atomic nuclei, up to the moment when the cosmic microwave background was released. We might understand dark matter's nature, knowing what particles comprise it and how they were produced in the early universe. We might even understand dark energy, the mysterious force accelerating cosmic expansion, if it turns out to connect to the same physics that explains baryogenesis. This would be a remarkable achievement, a level of understanding of the universe's fundamental workings that would have seemed impossible just a century ago. We would have a coherent picture stretching from the smallest scales to the largest, from the first moments of time to the present day. The limits of knowledge. But even this grand unified understanding would have limits. There would still be questions it couldn't answer, mysteries that would remain. Why did the universe begin? What, if anything, came before the Big Bang? Why are the laws of physics what they are? Why does mathematics describe reality? Is our universe the only one, or is it part of a larger multiverse? Some of these questions might be answerable by future science. The multiverse question, for instance, might be addressed if we find evidence that different regions of space have different physical laws or constants. The question of what came before the Big Bang might be answered by a theory of quantum gravity that describes the very beginning of space-time itself. But some questions might be fundamentally unanswerable, at least by the methods of science. If the laws of physics are just brute facts, if there's no deeper explanation for why they are what they are, then asking why might not have a scientific answer.
We'd be left with the laws themselves as the ultimate foundation, explaining everything else, but not themselves explained by anything deeper. This would be a kind of limit to scientific knowledge, not because of any failure of science, but because the question has moved beyond the domain where scientific methods can reach. Science explains the universe in terms of laws and mechanisms, but if those laws and mechanisms are ultimate, there's nowhere further for science to go. Philosophers and theologians might still propose answers to these deeper why questions, but those answers would be outside the realm of empirical testing. They'd be matters of interpretation, of worldview, of personal belief. Living with answers and mysteries. This coexistence of answers and remaining mysteries is something we'll need to be comfortable with. We'll know why the universe is filled with matter, but we won't know why there's a universe at all. We'll understand how particles get their masses, but we might not know why those particular mass values. We'll trace cosmic evolution from the first moment, but we might not know what determined the initial conditions. This is actually a familiar situation in science. We know a great deal about biology, but we don't fully understand the origin of life. We understand chemistry in exquisite detail, but we can't predict exactly what new molecules will be useful as drugs or materials. We can describe planetary formation, but we can't yet explain all the quirks of our solar system's architecture. Science provides islands of understanding in a sea of mystery. As those islands grow, touching and merging, the map of our knowledge expands. But the horizon of mystery expands too, as each answer reveals new questions we couldn't even formulate before. This isn't a failure, it's the nature of inquiry. A universe that revealed all its secrets immediately, that had no depths left to explore, would be a less interesting place.
The persistence of mystery, even as understanding grows, is what keeps science vital and exciting. The human element. Throughout this journey, it's worth remembering that science is a human endeavor. The equations are written by people, the experiments are designed and built by people, the ideas are conceived in human minds. The search for understanding is, at its core, an expression of human curiosity and creativity. The scientists working on the matter-antimatter mystery are not abstract entities, but individuals with lives, hopes, frustrations, and inspirations. They spend years designing experiments, debugging equipment, analyzing data. They collaborate with colleagues across countries and continents. They teach students, write papers, apply for funding. Some of them will be lucky enough to make the crucial discovery that solves the mystery. Their names will be remembered, their work celebrated. But thousands of others will have contributed in essential ways, building pieces of the apparatus, developing analytical techniques, ruling out wrong paths, preparing the ground. This collective effort is one of humanity's noblest undertakings. It requires cooperation across borders and cultures, the sharing of knowledge freely, the subordination of ego to truth. When the matter-antimatter mystery is solved, it will be a victory not for any individual or nation, but for humanity as a whole. Communicating understanding. One challenge that will arise as we deepen our understanding is communicating it. The physics of baryogenesis is already quite technical, requiring years of study to fully grasp. As we probe deeper, the mathematics becomes more abstract,
the concepts more divorced from everyday experience. How do you explain to a non-physicist why supersymmetric partner particles are necessary? How do you convey the elegance of gauge unification? How do you describe the quantum fluctuations of the Higgs field during a phase transition?
This communication challenge is important because science is a public good, funded largely by society and conducted for the benefit of all humanity. People have a right to understand, at some level, what discoveries are being made and why they matter. Science communicators, educators, and scientists themselves will need to find ways to convey these deep ideas in accessible terms. Metaphors, visualizations, simplified models, all these tools will be necessary. And while these simplified explanations can never capture the full mathematical beauty and precision of the actual theories, they can convey the essential insights and their significance. This very exploration we're on right now is an example of that effort. We're walking through ideas that, in their full technical detail, require advanced mathematics and physics, but by using ordinary language, by taking our time, by building ideas step by step, we can grasp the essential story. The universe shouldn't exist according to simple symmetry arguments, but it does, and we're searching for the physics that explains why. Inspiring future generations. One of the most important impacts of solving the matter-antimatter mystery will be inspiring young people to pursue science. There's something captivating about a mystery that goes to the heart of existence itself, and its solution will capture imaginations worldwide. Some young person hearing about the discovery will be inspired to become a physicist. They'll want to be part of the next great search, the next mystery to solve. They'll study mathematics and physics, work through the difficult concepts, eventually contribute their own ideas to the ongoing quest for understanding. This is how science perpetuates itself. Each generation is inspired by the discoveries of the previous one and goes on to make discoveries that inspire the next. The solution of baryogenesis will be one more link in this long chain stretching back centuries and forward into an open future. And it's not just future physicists who will be inspired. Understanding how the universe came to be filled with matter will enrich our culture, inform our philosophy, deepen our sense of connection to the cosmos. Artists will create works inspired by these ideas. Philosophers will incorporate them into their thinking about existence and reality. Educators will use them to kindle curiosity in students of all ages. Science doesn't exist in isolation. It's woven into the broader tapestry of human culture, influencing and being influenced by art, philosophy, religion, politics. A discovery as profound as the solution to baryogenesis will send ripples through all these domains. The ongoing journey. Even as we look forward to solving the matter-antimatter mystery, we should remember that science is a journey without a final destination. There will always be new questions to ask, new phenomena to investigate, new depths to explore. After baryogenesis is understood, physicists will turn their attention to the remaining mysteries. Dark matter and dark energy will still need explanation. The unification of gravity with the other forces, the quest for a theory of quantum gravity, will continue. The nature of space-time at the smallest scales, the behavior of the universe at the largest scales, the possibility of other universes, all these questions will remain. And there will be surprises. There always are. Discoveries that nobody predicted, phenomena that don't fit into any existing framework. These surprises are what keeps science vibrant. They remind us that nature is richer and stranger than our theories, that there's always more to learn. The solution of one mystery opens the door to the next. This is the pattern throughout the history of science. When Newton explained gravity, it led to questions about the nature of space and time. When Maxwell unified electricity and magnetism, it led to questions about the speed of light and the nature of electromagnetic waves. When Einstein developed relativity, it led to questions about the universe's geometry and evolution. Each answer is a new beginning. Each solved mystery reveals new mysteries. The journey continues, generation after generation, always advancing, but never arriving at a final stopping point. A thought experiment. Let's imagine a future, perhaps a century from now, when the matter-antimatter mystery is long solved. Physics textbooks present the solution matter-of-factly as an established part of our understanding. Students learn about it alongside Newton's laws and Maxwell's equations as fundamental knowledge about how the universe works. In this future, what mysteries occupy physicists' attention? Perhaps they're working on a complete theory of quantum gravity, finally understanding how space-time behaves at the Planck scale. Perhaps they're exploring the multiverse, if evidence for it has been found. Perhaps they're investigating entirely new phenomena we can't even imagine now. Those future physicists will look back on our era, the early 21st century, as the time when baryogenesis was being solved. They'll read the papers describing the crucial experiments, the theoretical breakthroughs. They might wonder what it was like to work on such a fundamental problem, to not know the answer to why the universe exists. And they might reflect on how far understanding has come, from the ancient Greeks wondering about the basic elements, through the medieval period's gradual accumulation of knowledge, the scientific revolution, the development of modern physics, the solution of mystery after mystery, each generation building on the last, slowly constructing an ever more complete picture of reality. But those future physicists will still have mysteries of their own. They'll still be asking deep questions, still designing experiments, still proposing theories and testing them. The journey will continue, just as it has for us, just as it will for generations beyond them.
The privilege of wonder. There is something special about living in a time of active mystery solving. We are privileged to exist in an era when deep questions about reality are being actively pursued, when the tools exist to potentially answer them, but when the answers haven't yet been found. This is a sweet spot in the history of science, early enough that fundamental mysteries remain open, but late enough that we have the theoretical and experimental tools to address them. Future generations might envy us this position, much as we might envy those who lived during Einstein's era or when quantum mechanics was being developed. The matter-antimatter mystery is our generation's great puzzle. It's a worthy successor to the mysteries that previous generations solved, and its solution will be a worthy achievement to pass on to future generations. As you lie here, contemplating these ideas, you're participating in this moment of wonder. You're thinking about questions that go to the heart of existence, questions that the brightest minds are actively working on, questions that might be answered in your lifetime. That's remarkable when you consider it. You exist in a universe that shouldn't exist, and you have the capacity to wonder about this fact, to understand the problem, to follow along as scientists search for the answer. The universe, through you, is contemplating its own existence and its own mystery. The beauty of uncertainty. Before we move to our final reflections, let's appreciate something that might seem counterintuitive. There's beauty in not knowing. If we already understood everything about the universe, if every mystery had been solved, physics would be complete, but also, in a sense, finished. There would be no frontier to explore, no unknown territories to map. The thrill of discovery would be gone. The matter-antimatter mystery, precisely because it remains unsolved, gives us something to strive toward.
It motivates the building of new experiments, the development of new theories, the training of new generations of scientists. It keeps the field alive and dynamic. When it's solved, that particular source of wonder will be gone, replaced by understanding. But new mysteries will take its place. The frontier will move,
but it won't disappear. And we'll have the satisfaction of knowing that a deep question about reality has been answered, even as we turn our attention to the next question. This cycle of mystery and solution, question and answer, wonder and understanding, is what makes science such a profound human endeavor. We're simultaneously building a cathedral of knowledge and always finding new wings to add, new heights to reach. The personal dimension. Throughout this exploration, we focused on the scientific and philosophical aspects of the matter-antimatter mystery. But there's also a personal dimension worth considering. Why does this mystery matter to you? Not to humanity in general or to physics as a field, but to you personally, lying here, listening to these words. Perhaps it's the sheer wonder of it, the realization that your existence is both miraculous and unexplained. Every atom in your body is a survivor from the first moments of cosmic time, having escaped annihilation through a process we don't fully understand. Perhaps it's the intellectual challenge, the pleasure of grappling with difficult ideas and following chains of reasoning into deep territories. The human mind enjoys complexity, enjoys being stretched and challenged. Perhaps it's a sense of connection to something larger than yourself. By thinking about these questions, you're joining a community of inquiry that stretches across time and space, linking you to people throughout history who have wondered about existence and reality. Or perhaps it's simply curiosity, that fundamental human drive to understand, to know, to push beyond the boundaries of current knowledge.
Curiosity doesn't need justification. It's an end in itself, valuable because it makes us more fully human. Whatever your reason, it's valid. Science is for everyone who chooses to engage with it, not just for professional scientists. The questions belong to all of us, and so do the eventual answers. Practical implications for daily life. You might wonder whether understanding baryogenesis will change your daily life in any practical way. The honest answer is probably not directly, at least not anytime soon. Knowing why the universe contains matter won't change how you cook dinner or commute to work. It won't pay your bills or solve personal problems. In that sense, it's utterly impractical knowledge. But impractical doesn't mean worthless. Understanding for its own sake has value. It enriches life, providing a deeper context for existence. Knowing that you're made of matter that survived against impossible odds, that the universe went through extraordinary processes to create the conditions for your existence, this knowledge can be profound, even if it doesn't change your daily routine. Moreover, the indirect effects of this understanding might be quite practical over time. The technologies that emerge from fundamental physics research often take decades to appear, but they do appear. The computer you might be using, the medical treatments available, the GPS that guides navigation, all of these depend on fundamental physics discoveries made decades ago by people who had no idea their work would have such applications. So while understanding baryogenesis won't immediately change your life, it might change your grandchildren's lives in ways neither you nor the scientists working on it can predict. The ethics of knowledge. There's an ethical dimension to the pursuit of knowledge that's worth touching on. Should we spend resources on understanding the matter-antimatter asymmetry when there are pressing practical problems to solve? Hunger, disease, poverty, climate change?
This question has been asked throughout history whenever resources are devoted to fundamental research, and the answer that's emerged is that both are important. We can and should work on practical problems while also pursuing fundamental understanding. Fundamental research and applied research aren't in competition, they support each other. Practical problems often require fundamental insights for their solution, and fundamental research, as we've discussed, eventually yields practical applications. Moreover, the pursuit of knowledge is part of what makes us human. A society that abandoned fundamental inquiry to focus solely on immediate practical needs would be impoverished in spirit,
even if it solved those practical problems. We need both, the wisdom to address practical challenges and the curiosity to explore fundamental mysteries. The resources devoted to particle physics and cosmology are, in the grand scheme of government and societal budgets, quite small. They represent an investment in understanding, in human potential, in the future. It's an investment worth making. The interconnectedness of knowledge. One of the beautiful aspects of solving the matter-antimatter mystery is how it connects to so many other areas of knowledge. It's not an isolated problem, but one that touches on cosmology, particle physics, quantum field theory, thermodynamics, nuclear physics, and more. Understanding baryogenesis requires understanding how particles behave at high energies, which connects to the theory of forces and symmetries. It requires understanding cosmology and the universe's early evolution. It connects to questions about the Higgs mechanism and how particles acquire mass. It relates to neutrino physics and possibly to dark matter. This interconnectedness is typical of deep scientific questions. They don't exist in isolation, but are woven into a web of knowledge where each thread supports and illuminates the others. Pull on one thread, and the whole web responds.
This is why breakthroughs in one area often lead to progress in seemingly unrelated areas. Understanding is holistic. Insights in particle physics might inform cosmology, which might suggest new experiments in nuclear physics, which might reveal something about quantum mechanics. The solution of baryogenesis will send ripples through this web of knowledge, tightening some connections, suggesting new ones, perhaps revealing unexpected relationships between ideas that seemed separate. The role of failure. It's important to acknowledge that the path to understanding is paved with failures. For every theory that turns out to be correct, there are dozens that are ruled out by experiment or found to have internal inconsistencies. Scientists working on the matter-antimatter mystery have proposed hundreds of ideas over the decades. Most of them haven't worked out. Experiments have been built that didn't find what they were looking for. Calculations have been performed that led to dead ends. This is normal and healthy. Science progresses by ruling things out as much as by finding what's right. Each failed theory, each null result from an experiment, narrows the space of possibilities. It's not wasted effort, it's essential work of elimination. And sometimes the failures teach us more than the successes. A theory that fails in an interesting way might reveal something unexpected about physics. An experiment that doesn't find what it's looking for might discover something else entirely. The scientists who work on ideas that turn out to be wrong haven't failed as scientists. They've contributed to the collective effort, testing possibilities that needed to be tested. Their work is valuable even though it didn't lead to the final answer. Imagining the answer. Let's engage in a thought experiment. Imagine that tomorrow, a definitive answer to the matter-antimatter mystery is announced. Experiments have confirmed beyond doubt that a particular theoretical framework is correct.
How would you feel? There would certainly be excitement, the thrill of finally knowing the answer to such a profound question. There would be satisfaction at seeing decades of work come to fruition. But there might also be a touch of melancholy. The mystery that has driven so much research, inspired so many scientists, captured so many imaginations, that mystery would be gone, replaced by established knowledge. This is the paradox of inquiry. We work toward answers, but something is lost when they're found. The journey is often as meaningful as the destination. Of course, this melancholy would be brief. New mysteries would quickly fill the space left by the solved one, and the understanding gained would be so rich, so full of new implications, that there would be plenty to explore and wonder about. Still, it's worth acknowledging that there's something precious about living with an unsolved mystery, especially one as profound as this. We're in a unique moment in history, after the question has been clearly formulated, but before it's been answered. This moment has its own value. The cosmic perspective.
Let's zoom out one more time to the largest possible perspective. We've been talking about the universe and its matter content, but what is the universe really in the largest sense? It's everything that exists physically, all the matter, all the energy, all of space, all of time. It's vast, almost beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. It's been evolving for nearly 14 billion years, and it will continue evolving for trillions of years more. And all of this, every galaxy and star, every planet and particle, exists because of a tiny asymmetry in the first moments of cosmic time. One extra matter particle for every billion matter-antimatter pairs. And from that microscopic imbalance, everything emerged. It's humbling and awe-inspiring simultaneously.
The universe is so vast, yet it hangs on such delicate physics. Change the strength of the matter-antimatter asymmetry by even a small amount, and the universe would be completely different, perhaps empty of matter, or perhaps so dense with matter that it would have collapsed back on itself long ago. We exist in a universe that's finely tuned in ways we don't fully understand. The matter-antimatter asymmetry is one example, but there are others. The strength of gravity, the mass of the electron, the properties of the Higgs field. Change any of these by modest amounts, and the universe couldn't support complexity, let alone life. This fine-tuning is itself a mystery, one that might be connected to the matter-antimatter asymmetry, or might have a separate explanation. It's another question for future science to explore. Your place in the story, and where do you fit into all of this? You are matter that survived the first moments of cosmic time. The atoms in your body were forged in stars that lived and died billions of years ago. The oxygen you breathe, the carbon in your cells, the iron in your blood, all created in stellar cores and scattered through space by supernova explosions. You are quite literally stardust, cosmic material, organized in an intricate pattern that gives rise to consciousness, to the ability to wonder and understand. You are the universe becoming aware of itself, contemplating its own existence and its own mysteries. This isn't poetic exaggeration, it's literal truth. The matter of your body has existed since the first moments of cosmic time, cycling through various forms: primordial plasma, hydrogen clouds, stellar cores, supernova debris, interstellar dust, a molecular cloud, the solar nebula, the early Earth, countless living things, and now you. And somehow, organized in just the right way, this matter can think, can reason, can understand, can ask why the universe exists, and work toward answering that question.
This is perhaps the deepest mystery of all, deeper even than the matter-antimatter asymmetry. How does matter, organized in complex patterns, give rise to consciousness, to subjective experience, to the sense of being someone thinking these thoughts? Science is beginning to approach this question through neuroscience and psychology, but we're far from a complete answer. It's another frontier, another mystery for future generations to explore. The narrator's reflection. After this long journey through the mystery of existence, through the theories and experiments and philosophical implications, I find myself returning to a simple sense of wonder. We live in a universe that shouldn't exist, yet here it is, vast and ancient and beautiful. We are conscious patterns of matter, asking why we exist, using the very atoms that survived against impossible odds to contemplate the mystery of their own survival. The physics is intricate and difficult, the mathematics demanding, the experiments extraordinarily sophisticated. But at its heart, this is a simple story. The universe exists, and we want to know why.
I suspect that when we finally understand the mechanism, when the experiments confirm which theory is correct and the textbooks are rewritten to include the answer, we won't lose our sense of wonder. If anything, it will deepen. We'll understand how delicate the balance is, how precisely the physics must work for anything to exist at all. We'll appreciate more fully how remarkable it is that we're here to understand it. And then we'll turn to the next mystery, the next question at the edge of our knowledge, because that's what we do. We're pattern-seeking, question-asking, wonder-filled beings. We can't help but ask why, can't help but search for understanding. The matter-antimatter asymmetry is one question among many, but it's a profound one. It goes to the heart of what existence means, why there's something rather than nothing.
I believe, though I cannot prove, that understanding it will be one of humanity's greatest achievements, a moment when we glimpsed something fundamental about the nature of reality. But even if I'm wrong, even if the answer turns out to be simpler or more mundane than we imagine, the search itself has value. The experiments built, the theories developed, the ideas explored, all of this enriches human knowledge and capability. All of it is worth doing. We are lucky to live in a time when such questions can be asked scientifically, when we have the tools to potentially answer them. Our ancestors wondered about creation and existence, but could only speculate. Our descendants might know the answer so well that they seem obvious. We're in between, in the moment of active discovery, and that's a privilege. The final question. So let me leave you with this, a question to carry with you as you return from this exploration. If you could know with absolute certainty the complete answer to why the universe exists, every detail of the mechanism, every equation, every particle interaction that led to matter surviving and forming everything we see, would that knowledge make existence more meaningful or less meaningful to you? Would understanding the physics of creation diminish the wonder of being, or would it deepen your appreciation for the delicate balance that allows anything to exist at all? Think about it gently, without rushing to answer. Let the question settle into your mind. There's no right answer, no wrong answer. It's simply something to contemplate as you drift into whatever comes next. The universe exists, you exist, and somewhere between mystery and understanding, between question and answer, we find meaning in the simple fact of being. Rest now in this thought. Let it carry you forward. And perhaps when you're ready, wonder.